Okay, so as I was just saying, we're going to talk about orbital diagrams today. And so what these orbital diagrams are a way to describe where these electrons exist with a certain probability attached to it. And so there's mathematically, this is like a mathematically derived idea, but we're just going to focus on the concepts because this is not a quantum mechanics course. And so I'm going to kind of fill in a few things that you should know about orbital diagrams before we start. And so the next thing is that these boxes you see represent orbitals. Or what we call electron clouds. So they're just the spots that electrons can exist. We put them in what's called orbitals or electron clouds. And so the lowest energy, that's the lowest orbital. And as they increase in energy, it increases upwards. So down here is where the lower orbitals are, and then the higher energy orbitals exist. So there's kind of this increase in energy from bottom to top. So I'm gonna put that like this too. Remember that big E stands for energy. And then we need to know that arrows represent electrons. So what we're going to be doing is we're going to be filling in these boxes with arrows to represent the orbital diagrams for some of the basic elements here. And so we'll start with hydrogen. Now, hydrogen has the atomic number of what? Awesome. So if it has one proton. And in order to be neutral, then what does it also have? One electron. So that means we only have one electron to fill in. And so the key here is that we fill from the lowest energy first. So what I'm going to put is an upwards arrow in this box next to 1s. And so these number letter pairs to the left, we are going to call those our sublevels. So I call this my 1s sublevel, and this is an orbital box. The arrow is my representation of an electron. And so not only can we show it visually, we're going to write what we call an electron configuration, which is just a formula. So what we write is 1s, so we write the sublevel out, and then we're going to use a superscript to denote how many electrons are on that sublevel, which how many do we have? 1. So 1s1. That is our electron configuration for hydrogen. Are there any questions where I got either the 1s or 1 from? S has to do with the orbital shape, but we'll talk about that in a bit.
So that's just saying it was 1 electron?
Yep, so 1 electron in the 1s sublevel.
And the arrow is up because
It has to do with electron spin, which we'll talk about later too.
So the first one is saying that it's the first, like, what's it called, orbital?
Yep, the lowest energy, because we always fill the lowest available energy.
Okay.
All right, now we're gonna go all the way to the right and talk about helium. Because helium has what atomic number? So that means we have 2 electrons. And so if we fill, now we started with 1 up arrow. Now the other electron is gonna be a down arrow. And so like I said, it has to do with the spin. This is what makes these electrons happy. And so every box can have 1 up and 1 down arrow. So I'm gonna write that out. So that second arrow points down. And so if we were to write that electron configuration or that formula, it is 1s. Now how many electrons are in the 1s sublevel? 2. So our superscript is now 2.
I still don't understand what the arrows are doing.
So the way that electrons exist in space, they have a specific spin. They either spin up or spin down. And just because of how things are in one orbital, one's going to be up and one's going to be down. That's just how we fill it. Always.
Just because there's 2?
Yep. Because of math, pretty much. So.
Not like per orbital consistent throughout like all the elements.
Every orbital can only hold 2 electrons. That's the rule.
Even like the higher level ones.
Yep, because then they start getting different shapes and orientations, which we'll talk about.
How can hydrogen have 2 electrons?
It doesn't. Helium. We just did helium. Hydrogen only had 1.
That's why I was thinking, sorry.
Okay. All right. Are we good?
Yep, we're
Okay.
sorry.
No worries. Now we're going to move on to lithium. Lithium has the atomic number of 3, which means we have 3 electrons. And so we're filling 1s with 2 electrons. So 1 up, 1 down. Then we're going to move to the next lowest available energy level. In our case, that's 2s. So then we start again with that up arrow. So we have our 3 electrons on our diagram. Now our configuration is going to be 1s. We have 2 electrons. But in our 2s sublevel, we have 1. Follow me there? Okay. Moving on to beryllium. Beryllium has atomic number of 4. So that means it has 4 electrons. So starting with 1s, we fill 1s with 2 electrons. We are also going to think that next electron as the down arrow for beryllium here. So now 2s is full. And so how we write that is 1s2, because 2 electrons in 1s, 2s2, because there's 2 electrons in the 2s sublevel. Any questions about that one? Okay. I know, really riveting content here, guys. Okay. Boron has 5 electrons because of atomic number 5. So we start with 1 electron, 2 electrons, 3, 4. Now the 5th electron is going to go into what's called the 2p sublevel. 3s is higher in energy, and remember we wanted the lowest available. So where it's going to go is in this leftmost box. We're going to put an arrow upwards. Put the 5th one here. So those now s orbitals, there's only 1 orientation. That's why we only have 1 box. P has 3 different orientations. So there's 3 different orbitals. So we haven't talked about their shapes, but just know that you go higher in energy, things get more complicated.
Can that 2p level hold 6?
Correct. Right now, though, since we only have 5 electrons, we're just going to have 1 in the leftmost orbital. And so how we write this is still 1s with 2 electrons, our 2s with 2 electrons as well. But now our 2p sublevel just has 1. This is the, oh, I shouldn't put an arrow there, but still hanging on to you guys? No squinty eyes up there? Okay. All right, carbon. Carbon has 6 electrons. And so this one's important because this has to do with a rule here. And so we still fill 1s and 2s the same. And so where we left off is we had this up arrow in the leftmost box. Now, because the other 2 orbitals here are the same exact energy level, it's not going to cost any more energy to spread out. So think of electrons, they repel each other. And so it's this battle between, is it going to take more energy or occupy space? So when we have a bunch of orbitals that are the same energy level, it's going to spread out to save space. So we're going to actually fill an up arrow in the middle one before we start making pairs, okay? So the rule here is that electrons don't pair up. until all same sublevel orbitals have one electron. So what I'm saying is until all three of these orbitals have at least one electron in it, they're not going to start pairing up and making down arrows. Yes, JP?
So is an electron saying like it's an arrow?
Exactly.
Is electron matter if it's an up arrow or down arrow?
It does.
Well, like the electron can be an up arrow and a down arrow? Okay.
Okay, any other questions? Okay, so now when we move to nitrogen,
How would you write that?
oh, sorry, thank you. How this is written is 1s2, 2s2, 2p2, because there's 2 electrons in the p sublevel. And so we don't have to do any specification of how they're spread out because this is just how everybody writes it. This is the rule. Okay. Nitrogen. Nitrogen now has 7 electrons. And so how we fill it. And so I'm going to show you guys kind of a shorthand way that I like to do arrows. You can continue doing a full set of up and down arrows, but to save time, I use fishhook arrows. So that is up and this is down. And so it's a lot quicker to write. So if you see me start switching to this, it's habit. And so how I'll fill is 1s, 2s, and then now that takes care of 4 out of the 7 electrons, right? You follow me there? Because we have 4 arrows. So we have 3 more electrons to put. And so we put 1 in each box first. That gives us 7. And so our electron configuration, 1s2, 2s2, 2p3. Any questions on that? Okay, now when we add that next electron, because oxygen has 8 electrons here, this is where we start forming those pairs. So 1, 2, 3, 4 electrons, 5, 6, 7. Now that 8th electron, we're going to come back and make a pair in the first orbital there. Because now it has to. Because the competition between this 3s orbital and making a pair, it's going to pick the lower energy. That's why it goes there. So we get 1s2, 2s2, 2p4, because now we have 4 electrons. Fluorine, 9 electrons. So we start with 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, that doesn't look very good. 1s2, 2s2, 2p5. Neon, oops, I forgot to erase some of that. Has 10 electrons. Now we get 1s, which is a full sublevel, 2s, a full sublevel, and now our 2p sublevel is full as well. Neon adds that 10th electron, and so there's no more space. So this is important. Have you guys heard of noble gases before? At least heard of the term?
Yeah.
So neon, this is a noble gas. And the way its electrons are is Y. So what it means to be a noble gas is you are inert and non-reactive. And so, because the electrons, fill the sublevel completely, this makes it very stable.
Stable? Like what way?
Meaning, so what chemistry is the sharing of electrons. And so because its sublevel is complete, it doesn't want to give any away and it doesn't need to take any. And so it's very stable, so it's going to be non-reactive.
Do they give away and take anything?
Very rarely, no. They're very,
Paired up.
yeah, exactly.
So would be
So the last thing we talked about was Bohr's model, and it was great for hydrogen. So it only explained hydrogen's behavior. So that being said, that wasn't perfect. So we had to modify this and figure out our atomic theory to fit all elements. And so you might recognize the names of Schrodinger and Heisenberg. And so these are really the two that fought their way and did some crazy math and physics and calculus to figure out kind of the theory that we use today. So it is called the quantum mechanical model. Or it's also nicknamed the electron cloud model. And so if we think of this cloud model, what you have in your book is kind of a more simplified version. And so in the center, we still have our nucleus, but then we have like this cloud representation of where the electrons could exist. And so for this model, the more dense areas of the cloud, the more likely you are to find the electrons. And so this electron cloud, what it's telling you is that there's a 90% probability of finding an electron in it. And so this was determined mathematically. And so if we look at kind of a more complex idea, these orbitals that we talked about, so those boxes we are filling in with arrows, they actually have shapes to them. And so the more complex way to think about it is that this model describes the mathematical probability an electron will be found in regions called orbitals. And so what these orbitals are is, I'm gonna use this term superimposed, and it just means they're kind of stacked on each other and are among each other. So they're superimposed orbitals with unique shapes. And a key thing about these is that they're not just circles. And why this is important is because before we kind of described Bohr's model as like a planetary model, well, we're moving away from that. So instead of these electrons just moving in some circular path around the nucleus, they could be whizzing around in this infinity shape or just somewhere in a sphere. So we're going to kind of break off from this planetary model here. Okay, so the four biggest things that we'll make a note about orbitals is that it's the region of space where electrons are 90% of the time. They have different shapes. They can hold a maximum of 2 electrons. And those 2 electrons in orbital must have an opposite spin. Which is where we get the, oops, that's an awful arrow, up and down arrows when we were filling in those orbital boxes, is representing those opposite spins. And so if we take a step, or so if we like look at the shapes, now I'll show you a video here that kind of goes over them a little bit more visually, but we have, yeah, go ahead. Sure. We have what are called the SP, D, and F orbitals. And so kind of, I'm gonna give you guys a little word trick to remember them by. So S you can think of as the sphere. P you can think of as the peanut. D, this one's not the best representation, but think of it, I'm gonna kind of draw these lines here, as the diamond. But it looks more like a four-leaf clover. And then F I think of as flower. And so what I'm gonna do is switch over to my computer and show you guys this video. Hold on. Oh, sorry. Yep. Oh, I forgot to switch, hold on. So this is showing the S orbital as a sphere. So this is kind of all described among an X, Y, and Z axis. So think of it 3D. So in the center is the nucleus. The S was just that sphere around it. And then we have 3 different orientations. You can have the peanut shape. Think of each color as the one peanut along the X, Y, and Z axis. Then we have the DXZ, so they're showing you now the d orbitals one at a time. So this is that diamond or clover shape. So it exists among different planes. And so there's 5 different orientations for the d orbitals. So that's why you have 5 boxes for them. And then the last one looks a little funky. And so what this video will then show is kind of all these, how they stack and superimpose on each other. So starting again with that S, at the p orbitals, the 3 separate ones there. Here's the first 3 of D, dx squared, y squared, then the addition of dz squared. Back. Math. Trust me, there's so many things that I'm like, how are people this smart? It crosses my mind all the time. Okay, so thinking about the big picture, we're going to talk just a little bit more about this. Well, we can only have a maximum of 7 layers of an electron. And so we give a fancy name to each of these layers that these electrons can exist in. And so each is called a principal energy level, or PEL. And so when we start adding these layers is when we start to drop in rows of the periodic table. And so the fancy name for a row is period. But in parentheses, we can put row. So For example, hydrogen, helium are their own period. Then period number 2 starts with lithium, beryllium, and so forth. So as you go down the periodic table, you're adding these layers that these electrons exist in. And so each one gets more complex. And so starting with the first principal energy level, if I can zoom out here, that has just the s orbitals. So if we look over on the right-hand side, the 1 here, that represents our energy level, and we only have our 1s. Then the second, we can have both s and p. So we have a 2s and a 2p. The third, we add the d orbital here, and so we have a 3s, a 3p, and a 3d. Fourth sublevel, we add s, p, d, and f. And now for the 5th, 6th, and 7th, they can only hold, they also have S, P, D, and F. It doesn't add more funky shapes. And for the scope of our class, we're not going to really be getting into those extreme energy levels, those outer ones. We're going to stick to the more basic ones. And so to summarize this, yeah, go ahead.
Why is the D after the next layer of S?
What, like, what?
So it's 3S, 3P, and then 4S, and 3D.
Yeah, so
3 after 4S.
We'll talk more about that when we get into the transition metals configuration. It just so happens with how they're superimposed that it takes less energy to occupy the 3D orbital than it does to get to the 4P. So for the different orbital types, for S, we only have that one orientation, or the sphere. So up here, this is just the S orbital. It is just the single sphere that covers all 3 axes. The max number of electrons, well, since it only has that one orbital orientation, it can only hold 2. This starts at energy level 1. Then for P, we have 3 different orientations. So if we look at the boxes over here, what these actually represent are the P orbital along the x-axis, the P along the y, and the P along the z. Or if you look at my desk, it's the P along the x, the y, the z, okay? So these are the 3 separate boxes or orbitals. Then the max number of electrons for the whole P sublevel is going to be 6, because each one of these 3 orientations hold 2 electrons. This starts at energy level 2. For D, we have 5 different orientations. Each of these still can only hold 2, so it is a max number of 10 electrons. We don't start seeing this till energy level 3. F has 7 different orientations with a max number of 14, starting at 4. But like I said, we probably won't really get into the F orbitals here for the scope of this class. And so what these electron configurations are, just think of them as a summary. This is just how the electrons arrange within the orbitals. And so recall that the electron configuration, so I'm going to bring back magnesium, is the 1s2, 2s2, 2p6, 3s2. So when I say electron configuration, it's this formula. What's really cool about this is that you can identify elements by adding the superscript. And what I mean by that is if we add up 2 plus 2 plus 6 plus 2, that equals 12. Well, if we have 12 electrons, our atomic number is 12. Which element has the atomic number 12? Magnesium. So we're actually able to identify the element just by adding the total number of electrons. And so we can abbreviate this electron configuration to be even more of a shorthand. And so if we think about where magnesium is, if you look at neon, neon's number 10 on the periodic table there. To get to magnesium, you add 2 more electrons, right? Because neon has 10, magnesium has 12. Well, what shorthand can do is you can abbreviate to the noble gas before it. So in our case, how they show that is with brackets. Then we write the symbol, because neon is the noble gas that comes before magnesium. That takes care of everything up until the 2p6. Now we just have to state that it's those 2 other electrons in the 3s sublevel that come after. And so this is equivalent to the long form. It's just a shorthand way, simplifying it, saying, hey, we know the configuration for neon, just add 2 more electrons afterwards. Are there any questions on that? Okay,